Okay, hello everyone. Uh, Today we are going to start a new topic, and I think that it will be our last topic in this semester. I don't think we will be able to cover the topic of virtual memory, but at least I will try to cover the physical memory today, and then we have one more lecture left after the Thanksgiving, so we can try to cover virtual memory, physical memory, complete the topic in that lecture. Okay, so until this point, we have covered in context of operating systems, what is a process, what is a thread, how we create multiple processes, how we create multi-threaded processes, how the operating system performs the scheduling of processes to increase CPU utilization. And also, we had a look at different synchronization mechanisms in the last topic. Right now, we are going to talk about physical memory. Why we need to talk about physical memory in context of operating systems? Because remember, we said that whenever we want to execute a program, so the program is nothing but just a file sitting in the disk, right? So in order to execute that program, we have to load from the disk into the memory. And once it is in the memory and it has a process control block assigned to it, so we name it as a process, right? So program must be brought from disk and placed into the memory within a process context for it to be run. Otherwise, if we have not loaded into the memory, we haven't created a context for it. And when we say context, it's mean if the operating system is not maintaining all the information necessary to run a process, which means that operating system needs to maintain a process control block for it. So only then a program or a process can be executed, right? Or it can be scheduled by the scheduler for execution. So when a process is running, it can access main memory and registers directly. And by directly, we mean that the program or the instructions within the which are executed by the process, those instructions, those instructions can access data in registers or in the memory. For example, if you remember from your assembly language course, when you were working on the microcontroller, maybe you can recall that there were instructions which were either loading data directly into the registers or they were loading data in the registers from the memory, right? So that data, and then the instructions, for example, let's say if you want to perform add operation or and or on data, so that data was always read from registers, right? So the data either is directly read from the registers or first it is read from memory and placed into the register and then operation is performed on it. So it's mean that a process can read data only directly from memory or the registers, but it cannot access the data directly from the disks because there is no such instruction through which we can specify, okay, go to this particular block of the disk and read the data from that block, from that disk block. So, uh, register access. Yeah, so one thing, so now we know that the data CPU can access directly from the registers and the main memory. However, there is a big difference in terms of performance, or in terms of latency or time it takes to read the data from registers and the main memory. The data from registers is accessed, which means read or written, typically in a single clock cycle. However, if we want to read or write data to and from the memory, it takes many cycles, which mean it is more expensive in terms of required time delay. So that's why what we do is that we place the caches between the main memory and the CPU. Actually, caches are also a type of memory, but that caches are built on the same chip as the microprocessor or the or your core. So as a result, it is much faster since the caches and the CPU are on the same chip. It is much faster to access the data for the CPU from caches as compared to the memory, because memory is on a separate chip, right? So transferring data between two chips, it takes much more time as compared to transferring data between two components residing on the same chip. Okay, now since uh, we have multiple processes, if ideally we want multiple processes to be loaded in the memory in multiprocessor systems, because we have multiple cores and we want to run multiple processes, so we want multiple processes to be loaded in the memory. However, when we do that, we need to be sure that one process does not uh, access the memory which is allocated to other processes. So in other words, we want to make sure that a process can access only its own memory, the memory allocated to it, and not the memory of any other process. So this is what we have, what I have explained until now. So initially you have an program or executable file residing in the disk, and when you want to execute that program, the executable file must be loaded from the disk into the main memory, and then we after only it's loaded in the main memory, we name it as a process. Uh, and once it's loaded and it is scheduled for the execution by the scheduler, after that CPU can read instructions and the data from the process residing in the main memory, from the code residing in the main memory. And then as I said, we have caches in between, so that we can speed up the access to the data. Again, it's not shown in the figure, but caches and CPU, they reside on the same chip, and that's why accessing data from caches is much faster as compared to accessing data from main memory. So if we, as I said, if we have multiple programs started, which mean we can refer to them as processes. So if we have multiple processes running, it's mean they share the main memory. And then it should not be possible for one process to access memory of any other process or the memory which is assigned to the operating system. Why? Because if that happens, then one process, let's say process A, accidentally or by intention, it can corrupt the other execution of other processes, or it can even corrupt the execution of the operating system, right? If it is possible for one process A to, for example, write the memory which is allocated to other processes, or the memory which is allocated to the operating system. However, uh, we allow the operating system to access everything. By everything means that we allow the operating system to access all the memory, which means the memory which is allocated to the operating system itself, and the memory which is allocated to the other user level processes. And actually we should do that. Why we should do that? Because if we don't give this level of privilege to operating system, then it cannot do many of tasks which is it is supposed to do. For example, remember what happens when there is a context switch. So let's say if a process A is running, right, and a context switch happens, now what will happen, that the context of the process A is saved in memory. And when we say the context of process A is saved in memory, it's mean that value of the registers which are used by the process A, those are saved, its program counter is saved, all related information which we, for example, the IDs of the files which were opened and which were being accessed by that process A, those IDs of our file descriptors of those files are also need to be saved in the memory, right? So it's mean who is going to save it? The operating system is going to save it, all that information in the process control block, which mean that operating system need to access, it need to have the permission to access the memory which is allocated to the user processes. Otherwise, it cannot perform the context switching. And as I said, program or process, a user level process is allowed to access the physical memory allocated to itself only. uh, for uh, for this protection, and by protection which mean to ensure that a user level process can access only its own memory. So to enable this protection, we need the hardware support. Otherwise, it's difficult to ensure that a process is allowed or is actually accessing only its uh, own allocated memory. So how can we enable that protection, right? So there are various ways, but we are starting from the very simplest version of that protection, to just to like give us an idea. Uh, what we can do is like we can use two registers specific for each process. So actually not specific for each process, but what happened is that we have two registers, and these registers are named as base and limit registers, and they are loaded with the values specific to each process when a process starts running. Okay, so base and limit registers definitely they reside in the CPU, and they can be used as a simple protection mechanism. How? Uh, Before explaining how, let's first have a look what is like meaning of base register, or what do we hold in the base register. So this register actually contains the starting physical address of a program to run, and by physical address we mean uh, yeah, let me select the pointer and explain. So if you have, let's say this is your memory chip, right? And I don't know, let's say that size of this is only 100 locations, right? So address of each location is known as the physical address, right? Physical address. In comparison to physical address, we have logical address. So physical address mean it is the actual address which identifies a location in your actual memory chip. Uh, the opposite, or let's say, and a different idea is the logical address, which is used by the programs, but which doesn't identify any location, any actual location in the physical memory. We will talk about it in a minute, but let's say we just keep it simple. So suppose you have a memory which has addresses from 0 to 100. So each of that address is a physical address because it actually identifies location. So in base register, what we do is that we contain the starting physical address of the program to run. So it is basically the first address of the first instruction in the program, right? And limit our bound register, it contains the size of the program, right? So we have a figure in the next slide, so it will become clear. So hardware, then to enable the protection or to provide the protection, the hardware, what does it do is that it checks every address to be in the range. So, so So a pair of base and limit registers together they define the physical address space of a process running in the space. So for example, if you are saying that base register is let's say 10 and the size is limit is let's say you are saying 20. So the smallest address will be 10 and the maximum will be 10 plus 20. 10 plus 20 which is equal to 30, right? So the physical address space is basically the range of all the physical addresses which are generated or which are possibly accessed when a program is running, and you can get it by looking at the value of base register and the limits. So if the base is again, if base is 10 and limit is 20, so the first address will be 10 and the last will be base plus limit, which is 10 plus 20, 30. So the physical address space will be from 10 to 30. Physical address space of that particular process will be 10 to 30. So R, if let's say R is the value in the base register, L is the value in the limit registers, the physical address range will be from R to R plus L. So here is an example. Let's say if you have multiple processes located in the memory along with the operating system, right? And let's say you have like let's say process A, process B, and process C, right? And let's say the process B is loaded in the memory starting at address of 4200940 up to the physical address. It occupies this physical address 3040, right? So then when this process will be running, actually when the scheduler will schedule it for execution, again, remember, scheduler is a component of the operating system. So what will operating system do at that time? It will load the base register with the starting address of the process in the memory, which is in this case 30040, and then it will also put the value for the value for the size of the process in the limit register. So which in this case is 1200090. Now if you add limit to the base address, so it is 4209040, right? So, and as we will see in the next slide, this we will see how base and limit register then help in identifying or then uh, detecting any access if a process is trying to make an access to an address outside of its allocated memory locations. Again, these base and limit registers, they are on the CPU, right? So our process can then only access that range, only this R to R plus L, right? Access to outside the memory range, if the process B is running, let's say, so then it is allowed to access only the range starting from the base up to base plus limit, which is then comes to this exactly this value, right? So if it tries to make any access outside of this range, for example, let's say in this area or in this area or in OS area, then it will result in a memory error. Again, remember that on CPU, you have not, let's say, one pair of base and limit register for each process. But what happens that when a process starts running on a core, the base and CPU, the base and the limit registers on that core, they are initialized with the value of the base and the size of the memory which is allocated to that process. So, for example, let's say if the process A was running, then this base register here, it will be loaded with the value 256000, right? And then limit will be set accordingly. I don't know what is this limit, but whatever it is, if we know, we can simply put that value in the limit register. So now the question is that how then hardware memory access protection works with base and limit registers. So for that, base and limit registers, as I said, are set by OS upon context switch. So whenever, let's say here, this scheduler schedule the process A for execution, it definitely it's mean that a context switch happened before that some other process was running, and now process B is selected for execution. So at that time, when context switch happens, the base and limit registers will be loaded with the appropriate values according to process B. So then what happens that during the execution of, let's say, the process B, all the addresses which are generated by the process, definitely they are, because the process is running on the core. So those addresses are generated on the core and then sent to the memory, right? But while they are sent to the memory, before being sent to the memory, what happens that a check is made. So if the address generated by the process, if it is great, first we check, is it greater than or equal to the base value, the value stored in the base register? If no, it's mean that if it is less than base, then it's mean that an illegal address is generated. For example, here the base value is 30040. If now if the process B, while it is running, it tries to access the memory location, let's say less than, let's say 30039, which belongs to process A, right? So since it is less than the base value of the base register, it's mean that an error will be raised, and then operating system will take care of that error. So first we check whether that address is greater than or equal to base. If no, then error is raised. If yes, then we make the second check, which is that the generated address, is it less than base plus limit. If it is less than base plus, if it is not less than base plus limit, then again it finds that it means that it is an illegal address, and operating system is supposed to take care of that. But otherwise, it's mean that the address is within the range, and only then it is allowed to make an access to the memory. Otherwise, access to the memory is not allowed because address is not legal. Any questions?
Pretty
Okay.
straightforward, just needs to access within the range or else it causes an error.
Yeah, yeah. Every time we just make a check that it should be in the range. And by we, it's mean the hardware makes the check. Okay, okay. So now let's try to ask another question in terms of process execution, and more specifically in terms of how the memory is accessed when a process executes its instructions, right? So in a program, again, process is nothing but a program which is loaded in the memory and has its process control block, right? So in a program, you can have multiple variables and you can have multiple functions, right? So when code is generated, we use memory addresses for functions and branching, for example, are jumping, right? So, for example, if you let's say even if you are writing the assembly code for branching, you will be using labels. For jumping, you will be using labels. For functions, you will be using labels. And for example, if you remember the assembly programming for AVR microcontroller, you can define uh, symbols by using the directive EQU or equate, which is like give you a sense of the variable, because then you can say, okay, if I'm equating x comma something, so you are using that variable in your program, right? So, and even if you are not writing in assembly but in higher level language, so this is like typical, you will have variables and multiple functions. So these addresses uh, can be that now definitely if you are making, if you are having variables and functions, so it's mean that you need to know when I say you need to know, it's mean that when the program is executed in the hardware doesn't know anything about the variable name x, for example, or your function, for example, foo or my function, right? So it's mean that name of all those variables and all those functions, they need to be translated to the addresses. For example, when you say store value of 10 in X, so basically what you are saying is that store value of 10 at some memory location which is referred with the name X, but your hardware doesn't know nothing about name X. So that X needs to be translated into the address. Similarly, when you are saying, okay, call the function foo, right? So your hardware doesn't know nothing about the name foo, so that name foo need to be translated into a memory address where the code of that function is located, right? So those addresses, the addresses are memory locations where where your functions are variable are located. Those addresses can be physical or logical memory addresses, right? So by I have given you a crude understanding of what is like physical address. So physical address is the actual address in the memory chip which identifies the memory location. On the other hand, a logical address, uh, it is the address which is generated by your CPU, right? But this address is not the same as physical address. If it is not the same, then what's the point of having the logical address? Because it gives us some flexibility. Uh, and we will see what type of flexibility it provides us, right? But at this time point, it is sufficient for us to know that logical address is the one which is generated by the processor or the core, and the physical address is the one which is actually used to access a memory location, right? And like most of the time, like especially in modern systems, logical address and physical addresses are not same. So it's mean that we need to the process the logical address which is generated by the processor, we need to map it to a physical address. How? We will see in a while. So in very early system, they are just physical memory addresses. There were no relative addresses. So the problem with that was the problem with using only physical addresses and having no concept or no idea of logical addresses was that a program has to be loaded to that address to run. So, which, for example, if we are saying that we have variable x, and when we convert it into the machine code, so we always use the physical address and not the logical address. And let's say we use the physical address 100, right? So now, if I'm saying like, okay, move, uh, not move, let me check if I can use an instruction from the AVR microcontroller. Uh, yeah, for example, if I'm saying load uh, R16 x, right? Now you remember that x, if I don't know if you remember or not, but you can trust me for now that x need to be a physical address. So let's say 100. So it's mean that all the time you are reading data from the exact place from the 100. But let's say uh, if next time if you want to change the location of this variable x, then it will not be possible for your program will not work. So this is because we are using only physical addresses, and here is an example. Uh, like no, not in upcoming slide we have an example. So uh, okay, now remember we said that when you have a program, you can have different instructions, and then those instructions they possibly access the data from memory, right? Now let's say you have a high level statement x is equal to y plus z. Now in assembly language, when it will be translated to assembly, it will result in multiple instructions, right? So but this program when it runs before it is being run, we need to know where is this instruction or x is equal to y plus z, this statement is located in the memory, right? Is it what is its exact location in the memory, right? Similarly, if this instruction is now accessing the data x, y, and z, so where is x located, where what is the location of y, and what is the location of z, right? So how like when you as a programmer you write a program, and to the point where your program is actually running, in between you need to resolve these questions, like where what is the exact location of the instruction in the memory, because if you don't know that location, then when I said you, it means CPU. If CPU doesn't know the location of the instruction in the memory, it cannot fetch that instruction, and then it cannot execute that instruction. Similarly, if it doesn't know that where in memory the variables x, y, and z are located, it will not be able to read them and will not be able to perform the computation, right? So address binding of instructions and data uh, in your program or in your source code to the physical memory addresses, uh, it can happen at three different times. So actually we are trying we need to bind, or we need to know the address of each instruction and its address of each data in our program. But how can we, like, at what time this binding is established, right? At what time we find we can replace these question marks with the actual memory addresses, right? So there are three different options, right? One possibility is that these address binding happens at the compile time, which basically mean that uh, once you have compiled your source code into the object file, so in the object file, the absolute physical addresses are used. The physical addresses mean the exact location in the memory where your instructions or data are resided. So those addresses are used in your program, right? So the machine code, that is the object file generated by compiler, uses absolute addresses if physical address is known. But this can happen only when you know in advance where you want to load your program in the memory. Like, for example, if you want to load it here, or you want to load it here, or you want to load somewhere else, right? So if you know the exact starting address of your program in advance, so then you can actually write your code by keeping in mind that address. And then after when you compile your when you will compile your program, all the addresses will be known at that time. Again, I want to give you the example from your assembly course. If you remember, you were using the directives like dot text and dot data or dot org. For example, if you are saying dot org 100, and then you are writing your code, so the first instruction which you write will go to the address 100. Right now you know the absolute address, right? So since you know the absolute address, your when you compile it, then and the machine code is generated, now that machine code will be using the absolute physical addresses. The other situation is where we don't know at compile time the location where our program will be loaded in the memory. Will it be loaded here? Will it be loaded here, or will it be loaded here? We don't know at the time when we are writing the program. Since we don't know, so when we compile it, it is the compiled version of the machine code generated by the compiler does not uses the absolute physical addresses, because as a programmer, when I was encoding my code, I didn't know what is the starting address of my code, right? So then what does compiler do? It generates a relocatable version of the code, right? So for example, if you are writing a program, uh, for example, if you are writing a program and in your program you are saying, again, I can give you an example of so let's say you said first, okay, maybe I can go to the OneNote. That is easier. So to give you an example of the first case where your binding is resolved, binding between those variable names and function names and their addresses is resolved at compile time. So let's say if you have uh, a code of like this form, you are saying, let's say .org, I'm writing in assembly. You are saying .org 100, and then you are saying, okay, uh, I don't know, mm, move in R16, let's say R17, and then you are saying, okay, load immediate, and R17 something, let's say 10, and here I'm just putting a label, let's say label L1, and then you are saying jump L1, right? Now, since while I'm writing the code, this is the code I have written as a programmer, right? So, and I know that where the address, where the first instruction will be stored. The first instruction will be stored, this will be stored at address 100. And let's say if each instruction is 2 byte long, uh, let's assume each instruction is 1 byte long. So the next will be 101 and the next will be 102, right? So now when the compiler will generate the code, what it will do, it will replace uh, symbols with the exact physical address. Uh, Load immediate R1610, and here it will say, okay, jump to address 102, right? So because it knows that this program will be loaded at the address 100, right? However, so it's mean that the binding will be established at the compile time. Compile time mean once once the program is compiled, right? The other case is, let's say we don't know where the program will be loaded, right? As a programmer, I am not specifying it, and let's say it is the decision made by my loader, right? And I am not specifying where to load it. So loader makes the decision where to put it in the memory, right? In what address, right? So if that is the case, now the compiler, it cannot use 102. Why? Because uh, this code this code will work only if in memory, uh, in memory my first instruction is at address 100, second is at address 101, and third is at 102. uh, Sorry, here it should be not 102, it should be 100, right? So only then this program will work, right? Because here I'm saying jump to 100, right? Uh, but if again, if I said, if we don't know, if we haven't specified and we have left it up to the loader, so then compiler cannot create this type of code where it is using the absolute physical addresses. Then what it will do is that it will generate a relocatable version of the code. So where it will basically be saying move R16, R17, and load immediate, and R16 and 10, and then in jump it will say something like jump back by 2 bytes, right? And those 2 bytes can be like anything, like jump back, like whatever your current location is, go back by 2. Now this program will work when it will be loaded. It will work when the first address instruction is at address 100, and it will work even when the first instruction is not at address 100. Let's say it is at address 200, second one is at 201, and third is at 202. Still this program will work because we are simply saying go back by 2 bytes, right? However, then so compiler will generate this relocatable version of the code. So but what about our original question, which was like when the binding will be established between the symbols and the absolute addresses? It will be established at the load time when this program will be loaded in the memory, right? So when it is loaded in the memory, then when if loader is loading the program at address 200, so then this third instruction will basically become jump 200, because 2 bytes back is basically 202 minus 2 is 200, right? And if this program is loaded in the memory by the loader not at address 200, uh, but let's say starting at address 400, right? So the last instruction will become jump 400. So the addresses will be resolved at the load time. So where were we? I think on the next slide. Yeah, yeah. So binding and load time, compiler generates relocatable code, and the loader modifies addresses with respect to the starting physical address. So if the starting physical address is 200, then because our jump statement is go 2 bytes back, so it will be replaced by jump 200. If starting address is 400, our jump instruction was saying okay, jump to 400, right? Because our code is written in a relocatable way. Third thing is like uh, third option is, the third way is that this binding of the binding between the function names or variable names and their addresses is established at the runtime. So program has, again, this in this case in the logical addresses, and mapping from logical address to physical address is done by hardware at the runtime, and program can be moved around at runtime. So why we do this at execution time, in what situation? Just like I told you, like when we are not able to know this address, when we are writing the program, we haven't specified that where to load, and we then the compiler cannot use the absolute address, so it generates the relocatable variant, and then the loader establishes the binding at the time when it is loading. Similarly, there is a reason or a situation where we need to use the runtime binding. And what is that situation? So let's say you have this program. Maybe I can simply use the same code, which was, let's say, move R16 R17, and then load immediate R17 10, and then jump L1, right? And this is L1, right? So let's say you have you have like uh, uh, you have loaded this program into the memory, let's say starting at address 100, and so it takes 3 bytes, right? So, but remember, in memory, we are not holding only one process, we are holding multiple processes, right? And let's say that somehow the memory that is allocated to this process is not initially at time one, the memory allocated to this process is contiguous, which means from continuous from 100 to 102, right? But let's say at some later stage, because of no availability of contiguous 3 bytes, what does the memory allocator do is that it allocates 2 bytes at a contiguous location, and the third byte at a different location, right? Let's say the first instruction is placed here, move R16 R17, and then, sorry, load immediate R17 10, and then the third instruction is placed here. Now, what should, at in the first stage, or like, let's say an earlier time of first, when it allocated the memory, so here the address that was used, we can say it was 100, right? But now the address that is used, now let's say if this is at address 200 201, and this is 250, so then it should be 200, right? And next time, let's say if there is another situation where the whole program is mapped at a different location, then this address can change, right? Let's say it is jump 400, right? So how it can possibly change? Because there can be situation where we cannot find the sufficient contiguous space in context of this example, and then we allocate a third byte, let's say from a different location, or 2 bytes at, let's say, address one is at address 200, the other byte is allocated is at address 300, and the third is allocated at address 400. So then depending upon where is your first instruction or the label where you want to jump, depending upon that, you need to update this address every time, right? So that's why what we cannot know the target address uh, until we know that where is this label one located, right? And since during the execution of the program, the location of this instruction can, if we are saying that there are situations where we need to change the location of this instructions during the execution of the program, then it's mean we also need to, during execution, we need to change this address every time a location of this first instruction changes, right? So that's why if that is the situation, then we cannot resolve this redress uh, until we are running the program, right? So that's why we know that we say that the addresses are resolved in this particular situation at the runtime. We cannot know this address where the target address is, where the program is moved around during execution. We cannot know these addresses at the compile time or at the load time. So program has logical addresses, and mapping from logical address to physical address is done by hardware at runtime because the program can be moved around at the runtime. Okay, the here is an example to understand or to actually internalize what we have seen in previous couple of slides. So suppose that on the right side we have RAM or random access memory, and we have the physical addresses going from 0 to 44. So each address actually covers 4 bytes. So from 0, 1, 2, 3, they are indicated in the first they are indicated by the first address 0, and then next 4 bytes 4, 5, 6, and 7 are indicated by the address 4, and so on. On the left side, you have a program, and in this program, you have like instructions, a couple of instructions, uh, and then at finally you are saying jump to 12. So you are saying that okay, go to the first instruction. So actually there is a loop, right? So this loop will be executed in an infinite way, right? So now when you do the binding between the so actually you can hear also in if you are writing the assembly, so you will basically say jump L1 or some label, right? But then when you compile this program and the machine code will be generated, then that machine will code will replace L1 with 12, right? If we assuming if we know where the program is loaded, right? Like in assembly we said .org 100, for example. So then let's say this program is now loaded in the memory, and this program will work perfectly fine. So if the first instruction executes here, and every time our program counter points to the next instruction, which in this case is done by decrementing the address by 4. So what will happen, that first add will be executed, then move will be executed, then next instruction, so on. And then when you finally reach a jump 12, so you will go back to the first instruction, and there will be a loop, right? So this will work in this particular case. However, now if we consider the second example, let's say you have written a program, right? So this first program is same which we have seen in this previous slide. Now we have a second program, right? And this program is written assuming that this program will be loaded in the memory at the address 0. So if it is loaded into the memory at the address 0, it will work fine. Why? Because first this instruction will be executed, then sub, and then next one, and then finally when you go to jump 12, so it will go back here, right? So if now this program is loaded here, right, it will work fine, right? But again, if that is not the case, right, if uh, if our loader has no information about where the program will be loaded, then the program will not work correctly, and then we need to make our program relocatable. So here is the example. Let me simply erase these arrows not to confuse you. Okay, so now let's say both programs are loaded in the memory. So the first program is loaded started at the start of the address range. So it takes first 4 location, and then program 2 is loaded in the next 4 location. Now program 0 will work correctly because it is saying jump at 12, right? However, the second program, it is not relocatable. It will work only if it is loaded also in these first 4 bytes, because the program is not relocatable. Why? Because if you run this program now, what will happen? It will start executing this one, and when we say jump 12, so what we actually wanted is to go back the first instruction. But here the jump 12 mean basically going into the rest space of the program 1. So which is not what we wanted, right? So which mean that we have to change either we have to change this address, and for that we need to know where the program will be loaded in advance, so we can write like okay, jump 28 instead of saying jump 12, and then it will work correctly. Either we need to change this address, absolute address, physical address, and for that we need to know where the program will be loaded, The second thing is, if we don't know where the program will be loaded, we need to make this code or our program relocatable. How can we make relocatable? So for that, a simple way is that, for example, we can say, okay, add, we can give a displacement for every program. Like for example, for the program one, we are saying, okay, add 0 to every address. So then it will definitely go to, uh, this will go to address 0, this will go to address 4, this will go to address 8, and this will go to address 12, right? And for program, so it will still work correctly. But and for the second program, we can say, if we have a mechanism which adds 16 to every address, right? Then why 16? Because let's say if the loader knows that I have loaded the program one, and the first 16 locations, they are occupied already. So it can if it knows, and if it uses that information, so and then decides to add 16 to every address, so 0 plus 16 will become 16. So first, this jump 12 will be stored at the address 16, and in the same way all other addresses will also be changed to like 20, 24, 28, right? Now when you will run the program, what will happen, that when you have this jump executed, it will jump to the correct location and you will have the correct loop. Now, why is it possible? Why it became possible? Because now your program is made relocatable, right? In the previous where I was saying that we can replace 12 directly by 28, here again our code was not relocatable, but it will work only for the case where the program is loaded in, jump instruction is stored at address 16. So if we are writing 28, it will work only in that case. But let's say if I have changed jump 12 to jump 28, and then our program is loaded in such a way that our jump location is here of program 2, and saying jump 28, still it will not work, right? So our program is not relocatable still. However, if we have made our program relocatable, and then what will happen is that, uh, here we are adding 16, and if now let's say loader has in another case has already occupied these locations as well, so it knows where to put the first instruction of the next program, so it can change simply this 16 by another value, which is 32 in this case. Okay, so logical address space concept. Now, remember we said that we have on one side we have the physical memory, and all the addresses which are actually used to identify a location on that memory chip are known as the physical addresses. However, the addresses which are generated by a process running on a CPU, so which means the CPU sends out the address. So that address is your logical address. So the now the if we have these two different ideas of, like, logical address is a different concept than the physical address. uh, it gives us what flexibility? It gives us flexibility, like let's say if you have a process A, so process A will generate its logical addresses in a range 0 to max. What is max? So let's say if your address is, let's say I am saying 8-bit, right? Is 8-bit. So what is the total range of the addresses which you can generate? 0 to 255. So max will be 255, right? So all of them, process A, B, and C, they will be generating the addresses in the range, within the range 0 to 255. Any address will be within this range, and same for C, right? So these are the logical addresses. Now, if physical address is separate from logical address, then it gives us the flexibility that we can map, for example, the logical addresses generated by process A from 0 to 255 to an address range, let's say 100 to not let me say not 100, let's say 300 to 555, right? And how can I do that? For example, using the same idea which I gave you in the previous slide, you add 300 to every address which is generated by process A. So 0 plus 300 will be 300, 255 plus 300 will be 555. Now next time, if you want to, if there is a requirement and you cannot, it is not possible for you to put the program of process A exactly in that location. Maybe let's say it is already occupied by some other process in the memory. So you can simply say, okay, I will not add 300 to every address. Maybe I will address 600. Now your range will be, physical range will be from 600 to 855, right? So it gives you the flexibility of like where to place it, right? Uh, on the other hand, if we had no distinction between logical address and the physical address, which mean that the addresses generated by the process are exactly the same addresses from where the data and the instructions are fetched, it's mean that process A will always have its instructions and the data mapped in the address range 0 to 255, right? And then process B, since it also has the same address range, so all the addresses it is generating, they will also be falling in the same address range. All the addresses for process C will also be falling the same address range, which mean that at the same time you cannot run more than one processes. Even if let's say you have multiple cores, you have four cores, but you will not be able to run four processes on four cores at the same time. Why? Because all those four processes running on the four cores, the addresses they will be generating will be within the same range. So for example, let's say process A says, okay, I want to access variable X, process B say I want to access variable Y, and process C says I want to access variable Z. But now remember that they think that they are accessing their own data, but then in total we have only 255 memory locations. And if all those 0 to 255 are allocated to process A, how can process B puts this data into in the range 0 to 255, or how can process C can puts data in the range 0 to 255, right? So that's why we have these different two concepts of logical addresses and physical addresses, because then adding the displacement, different displacements, we can map those logical addresses to different locations in the physical memory. And in this way, we can have no overlap. But at the same time, processes will still be thinking that I am generating my addresses in the range 0 to 255. All of them will be thinking that our addresses are within the range 0 to 255, but the physical range where their data is mapped will be different depending upon the displacement added to their addresses. Any questions at this point? Okay, so we need logical address space concept that is different than the physical RAM or main memory address. I think I have explained it already. So a program uses the logical addresses and they start at zero, right? So zero, and the addresses which will be generated by a program will be in the range 0 to max. And what is the max? It depends upon how many bits are used to identify and address memory location. If 8-bit, it is 255. Let's say 16 bits, so you can do the math. I don't remember how to, like, you can simply convert it to raised to power 16 minus 1. Okay. So all addresses will be within that range. Set of logical addresses used by the program is known. So all this the set of the addresses that will be generated by the program, it is known will be known as its logical address space, and that the logical address space will be within 0 to max. Uh, what happened is that in this way, our memory is virtualized. And by virtualization, we mean that we have two different type of addresses, logical addresses and the physical addresses. And then we have a mechanism to map logical addresses to the physical addresses. So by virtualization mean, as I said in the previous slide, all the processes will think they are generating their addresses in the range within the same range 0 to 255, 0 to 255, but the actual physical addresses in the memory chip where they are located will be different for each one of them. Yeah. Okay. So what is logical or virtual memory layout of a process? So how the logical address space of a process is laid out. And again, when we say logical address spaces, the address range seen by the process are addresses generated by the process, right? So logical address space, as I said, is within the range 0 to max, and max is what, like if you have 32-bit address, so it will be 2 raised to power 32 minus 1 definitely. Uh, and this whole address space is then divided into different chunks or different sections. So stack, actually we have seen this division of memory layout in one of the previous lecture slides. So stack is the section which you use to hold the function arguments or local variables of a function or return values, right? And program code is, it actually holds your instructions. Data section, it holds the static data. It doesn't matter, it can be both type of both, like initialized or uninitialized. And heap is your section or part of the memory, which is used to allocate the memory dynamically. Like for example, when you use malloc in your C program running on Linux, so the memory which is allocated to your program is allocated from this chunk. Okay, and again, we are having all this discussion within the context of the logical address space, right? Logical address space. So and then stack grows downward and heap grows upward. Uh, let's not say upward or downward, but let's say they grow towards each other. So definitely when, for example, if in your process you have a if you let's say you have a variable x, right? You have a function and that function has a local variable x. So that x will be allocated an logical address space in the stack segment. But again, this is a logical address space. It will be first converted into the physical address space, and then that physical address will be used to access the actual location in the memory, right? Okay, so we have introduced the concept of logical and physical address spaces, and this distinction between logical and physical address space is central to properly manage the memory. Why? Because in modern systems, what happen is like the data, the data which you are reading from the memory are the program instructions which you are reading from when you are executing a program. Let's say you have uh, uh, let's say you have the CPU. Maybe I can go to the one note. It's easier to draw there. Or maybe I can stop because we have only 2 minutes before we go for the quiz. So I can start from the same slide next time. Why it is crucial to have two different type of addresses in modern systems, and I can explain it next time, right? So for now, do you have any questions before we go to the quiz?
I think I'm good. Thank you.
Okay, so if no question, then yeah, the quiz will be released in a couple of seconds, and then you can take it. Is the grade weighted in Canvas? I need to check, but most probably not. Most probably not. Okay. I'm not sure, but most probably it's not. So it is not your absolute score.